Alright, back again, but we got a short and sweet question, so let's get to it. Using the magnetic field of a dipole, calculate the average magnetic field of a dipole over a sphere of radius r centered at the origin. Do the angular integrals first, compare your answer with the general theorem of average fields, and explain the discrepancies. Then indicate how the coordinate-free form can be corrected to resolve the ambiguity at r equals 0. Evidently, the true field of the magnetic dipole is B dipole equal the coordinate-free form plus some delta term. And we should compare this to the electric analog. Alright, so in this case, and the integral is identical to the one in the electrostatic case. The resolution, same as before, is to regard the coordinate-free form as the correct outside the infinitesimal sphere centered at the dipole. Inside the sphere, the field is a delta function. Has some form A, delta cubed r, so three-dimensional, with A selected so as to make the average field consistent with the average field formula. So again, we see BAV is equal to 1 over 4 pi r cubed, and we need to substitute this in. And we see that here for A, we just evaluate at the origin due to the delta term. But we also know that the field with the dipole is equal to mu naught over 4 pi 2m r cubed. We now need to solve for A, which leaves us with 2 mu naught m over 3, simple algebra. So in order to add this in, in order to account for this, we just add this A delta term in, which is 2 mu naught 3m delta cubed r, and you're good to go. These deltas pop up everywhere. It's almost like if you don't see one, something's missing. But we have to take a look at the specific cases where we have infinities in the denominator, which is where deltas originally came up anyways. So be mindful of that with these coordinate-free forms, and more generally when you're dealing with fields that are considered average or dipoles. And yeah, you'll be good to go.